Thank you very much. Hello, so this is Victoria Spacer. I'm Associate Professor in Sustainability Research and Computational Social Science at the University of Leeds. And I'm sharing this first session where we're going to basically reflect on the outputs of this program from 2019, with Peter, Felix, and Paula presenting their results and giving you also a chance to discuss those as well. So if you have any questions, please do post them on Slido, and we can then pass them on to the speakers. And you can also always raise your hand if you want to ask a question. Thank you very much. And I will now hand over to Peter, who will then talk now about decision-making under uncertainty.
So I'm going to be talking about decision-making under uncertainty, and particularly decision-making under uncertainty for landscapes, which has some particular questions. So start off about decision-making. Making decisions is hard. It's very difficult. And I would say that all consequential decisions, all decisions that matter, involve uncertainty. I originally put all decisions involve uncertainty, and I thought, well, when I just choose which socks to put on in the morning, it doesn't involve uncertainty. But anything that matters does, or there isn't really a decision to be made. If it's obvious what we should do, then there is no decision making, apart from trivial decisions like what socks to put on. And the question is, how can we help decision makers make decisions? So I'm not a decision maker. I don't decide agricultural policy for the UK. You'll be glad to know. And I'm going to assume in this talk that there is a human decision maker who actually makes the decision. I'm not going to talk about algorithmic decision making where some computer makes the decision. Over the summer, we've seen that that's probably not a good thing. So I'm going to talk about supporting decision makers who are actually going to make that final decision, and how we can support those mainly in a mathematical way. I'll talk a little bit about non-mathematical things, but how we can support a human decision maker. Now it's up to them. They can reject what we suggest, that's fine, but at least we can give them some support from science and mathematics on what would be a good decision. So just to start off with a little bit of Bayesian decision theory, this is what we teach our third-year students. So we have some prior beliefs, which I'm going to express as a probability density function. We're going to be Bayesian, so our beliefs are in terms of probability. So we have some prior beliefs. We collect some data, which we again express as a likelihood, which is similar enough to a probability density function. We can conclude those. And then we use Bayes' theorem to produce some posterior beliefs. So we have some beliefs about decision-making things. We've collected some data. We've now got some distribution on those thetas. And now to make a decision, we've got a distribution. We have to make some decision. We introduce a loss function, which says how much we lose if we don't have the true value of our thing's theta. If you're an optimist, you have a utility function and you gain. But they're exactly the same thing. I just introduce a negative, a minus sign. And then we try and minimize our expected loss or maximize our expected utility. And that's just done here by this little equation here, which is just the expected value of the loss. So low probability things don't contribute to the loss, high probability things do. Now that's very simple and very easy, and is almost impossible to apply in real world situations. Now, if we think about decision making for landscapes, these are very complex decisions. I don't collect some data, modify my beliefs and make my decision. And since we're going into the future, we don't have any data on the future. So we replace data with models, and we have numerical models, and I've written some of the disciplines that these models come from. Ecology, agriculture, economics, climate, forestry. There's a longer list than that. We can write this list be very long, and we had long discussions about this a year ago. And all these things interact so that my agriculture model depends upon my climate model, but my climate model wants to pick up how much CO2 is being generated or absorbed by agriculture. So they all interact, but they're not usually in one single overarching model. And then just to make it more complex, they're what I'm going to call incalculables, things we can't put numbers on. And it pains me as a mathematician, but there are things we can't put numbers on. Now, we could argue about that. Some people claim you can put numbers on everything. You can put a cost on everything. We could have a survey and ask people how much they value the Lake District as a cultural place. But I think those numbers are different to the sort of numbers we would get out of a climate model. And we probably have to deal with those in a different way. And I'll come back to that later. So we've got these numerical models, and we have some form of uncertainty in those numerical models. Now, we've got no data, we've only got models. The quote from George Box, all models are wrong, but some useful. Now, most of our models are going to be deterministic, some might be stochastic. So we can split down the uncertainty we're getting from our models into various classes where it comes from. That comes from the fact that our models are wrong. They're missing processes, they're parameterizations. They are not exact models. Can people still hear me? That said, my fleshed up, okay, that my internet was unstable. So structural uncertainty is to do with the fact the models are wrong, and it's very hard to get a handle on that. Input uncertainty, so the inputs to the models are unknown. Well, we can deal with that. We have methods for dealing with that. I'm not going to go into that in detail. If you want to know, contact me outside this talk. And if we have stochastic models, then we have aleatoric uncertainty. The fact we run the model once, we get a different answer when we run it another time. Well, we can work that out. If we have infinite computer budgets, we can easily work those out. We can't work out the structural uncertainty. So what we can do is to talk to experts and ask them. Now that's hard. I've mentioned here expert elicitation. It's a well-studied problem. There are a couple of methods I've mentioned there. The Roger Cook method, where we actually calibrate the experts, and the Shelf method, the Sheffield elicitation framework from Tony O'Hagan and Jeremy Oakley. And there are others, but basically we ask questions to build up a picture of experts' belief as a form of probability distribution. And they're very cleverly worded questions so that we do actually get a reasonable picture of a PDF. Of course, if the experts don't know, we can't elicit that information from them. And in lots of these cases of how bad is your model, it's quite hard to get that information, particularly if you ask that question. If you ask, what processes are your model missing? How important might those be? We might be able to get a picture. But it's important to know that our models are all wrong. The real world is not a numerical model. So we're going to use models, which I've just said are all wrong. But we're interested in decisions in the future. We have no data. So we have no verification for the models. We can't check them. We can check them on the present day, but we can't check them in 20 years' time. And we can't post-process, which is what they do in weather forecasting, to correct some of those errors in the models from the experience in the past. So does that mean that we can't use models to help make decisions? Well, no, it doesn't, because the second half of the George Box quote is that some models are useful. The only problem is we don't know which ones. And in this case, it means we have to be more careful than we would be if we were making a decision on a weather forecast, where we're constantly checking how good the model is. And we have to elicit some of those uncertainties, particularly those structural uncertainties, because they're biases. So, but if we are careful and we explain to the decision maker what these issues are, then I think we can use models to help make decisions. Well, we can certainly use them to help make decisions. We can use them to help make better decisions. So how might we use these model projections to make decisions? Well, I'm going to create three methods because I've lumped everything into another one. We can look at scenarios, we can look at optimization, and there are other ways in which I will explain one possibility. So we can use the model to explore some future scenarios. So the classic example of this is the Climate Model into Comparison project, where there are a number of future storylines of possible futures of the world economy. And here's a plot from the IPCC showing the different storylines. So there's no, they're more than that. Sorry, there's 1, 2, 3, 4. Yeah, 4 storylines, these RCPs. And what we see here are the spread of the models around the for each of these scenarios. And that's quite nice. It gives us a picture of what might happen in the future if we followed these scenarios. But what it doesn't tell us, I'll put this line here, each storyline is treated separately. And you are not allowed, I put allowed in inverted commas because we do, to integrate across them to get other possible scenarios. So if I want to know what happens if I manage to go below RCP 2.6, there's no information here. And even if I want to go between this line and this line, I can't interpolate because I can't interpolate the story. I can interpolate the numbers, and I've done that, and it seems to work, but you can't actually interpolate. So if the story is important, you can't interpolate stories. We can't handle those in a mathematical way. And we know none of those stories are actually going to happen. To get this story is not the way the world is going to go. The world is going to go a different way. So they're limited use to a decision maker because a decision maker can't come and say what happens if, because we're limited to the scenarios we've done. So they're good for general advice, convincing people that global warming is a problem, this is fine, and it can give you some information on how bad a problem it might be if certain things happen, but it's not terribly useful for making a decision about how many trees we should plant or how we should cut emissions from cars. So an alternative to that is to optimize. So if you remember that little bit of decision theory I put up at the beginning, we were minimizing our loss. So we could try to do that. We try and find a course of action that minimizes some loss. And that will give us the best decision if such a thing exists. So if we can find an optimum, that's great, but it gives the decision maker no freedom. Because to find if we found the optimum, that's it. We've got the best, you can't do anything else. And decision makers like freedom, and this is where the incalculables and things come in because they factor those in. We can't do that if all we're doing is finding the best. What happens if things change between now and our optimum? We've lost the optimum path. So optima are a bit tricky. And the best decision, what are we optimizing on? Well, our objectives are rarely unimodal. So in the landscape, we might say, let's optimize on farmers' incomes. But that's probably not a very sensible thing, just to maximize farmers' incomes. We might want to maximize farmers' incomes while absorbing so much CO2 from forestry. And that brings us on to the idea of multi-objective optimization. And just here I've put two up from the IPCC. We might want to optimize on surface temperature, but at the same time, minimize sea level rise. In fact, those two, you probably do similar things. But farmers' incomes and absorbing CO2 from forestry may actually not be the same thing. So multi-objective optimization, instead of finding a single best point, we find what's called the Pareto front. And the Pareto front is, along that Pareto front, everything's an optimum of the two things combined. Okay? All are equally good. That's better than a single optimum, because now our decision maker only has to go along the Pareto front and choose the point they want. But it still doesn't take into account the fact that our models are wrong and the fact that things will change before we get to when if we're optimizing for 2050, between now and 2050, lots of things will change. So, is the best the enemy of the good? Should we be looking for the best decision you can make, or should we just be looking for good, robust decisions? Not necessarily the best possible outcomes. So here's my very badly drawn diagram. So here's the Pareto front down here. Along that line, everything's optimal. But in fact, this blue splodge here might all have good outcomes. They might all be acceptable outcomes, but they're not the best outcome. But they're good, they're fine. We could live with those outcomes. So something we came up with last year was actually thinking of this problem as an inverse modeling problem. So if this is my numerical model, this is my model of the economics of farming, in theory, I can produce the inverse model. So I'm going to go backwards. I'm not sure. I'm going to go backwards. I'm going to run my model backwards and see, for my outcome, for my farming income in 2050, what do I have to do to get there? Now, we can't do that analytically, almost certainly on the sort of models we're using, but we can produce numerical approximations to that. So we can use our inverse model to map the decisions that lead to good outcomes. So we found a set of good outcomes, and then we found a set of levers on the decision that will lead there. That's good for the decision maker, because now they have freedom. As long as they live in that set, we're going to produce something good, so they can take into account lots of other factors. And as we can track forward that set of decisions forward, and we can check if they need tweaking. Let's say someone comes up with a better model. We can inverse that and see, does that still work, or do we need to tweak our decision? So we can monitor it, and we can very easily change things as we go forward. So what about these incalculables? So there's qualitative information, which may be, we ask people to rank things, or there is totally incalculable stuff. What is the worth of an ancient forest? I don't think you can actually score that. Or an historic building, a cultural value. So what can we do about the incalculables? Well, we could quantify them, which is sort of making them from incalculables to calculables. It says, oh, an ancient forest is worth, 1 acre of ancient forest is worth 10 acres of replanted forest, therefore we can make trade-offs like they do with HS2. But in some ways, I think that's cheating. And some of these things really are incalculable. We can give the decision maker the room and let her include them. So they include them in some way in their head because that's what they do. They are decision makers. But I think there's an important thing that we should think about with qualitative information. It in itself is uncertain. And we need some way to include the uncertainty on that qualitative information as we feed that into the decision making. So in a sense, if we let the decision maker do it, they have to include somehow the fact that there is some uncertainty if you ranked the value of landscapes for their cultural or what's the right word? The fact that they're beautiful. That value, you might say that the Yorkshire Dales is worth more than the Lake District or the other way around, but that ranking is uncertain. And we have to include those uncertainties. We mustn't leave uncertainties behind. So, in conclusion, and I think this is pretty much what we thought about last year, decision making is hard. We shouldn't underestimate that, especially with a lot of uncertainty. Numerical models may be able to help, but they're not a panacea. Just for the fact you've got a model that it comes out of a computer with nice fancy graphics doesn't solve your problem. The models have their own problems. They can help, but they're not going to solve everything. If we're going to include uncertainty, we need to make sure that they're all quantified and included. And if we can't quantify it, we still need to include it. We need to say, we know this is uncertain. We don't know how uncertain it is, but it's there and you need to take that into account. We mustn't pretend. We need better methods. I think scenarios don't really work. Optimizing has a lot of problems. I outlined another possibility, but we've never done that with a big model. And I'm sure there are other methods that people could come up with that would be better or as good as that. And the final thing I'd like to say is I think we've got more questions than answers. Decision making under uncertainty is not a solved problem. Hopefully this week we can discuss that and maybe we can knock down some of the questions and come up with some of the answers. I don't know, but I will stop there. Thank you. So if Sherry?
I don't see any specific questions in the chat or on Slido at least as well. So we can either, if there are no questions immediate now, we can either proceed with the next presentation, maybe then just have the questions after all the speakers have presented and then kind of discuss them all together since it's all related. But I want still to give a chance maybe to ask if someone has a question to ask Peter. Okay, Brett has a question. Brett has raised a hand. Brett, if you can just unmute yourself and ask the question, please.
Can you hear me now?
Yes.
Brilliant. My chat's disabled. I don't know if that's true of other people, so wasn't able to put any comments on as we were going. Just a quick question, Peter, because it's something I've been wondering about. So this idea that you could sort of inverse the problem and start off by thinking about a lot of good outcomes and go back and say the policies that might deliver those good outcomes. There's this other aspect to it, which I'm not certain how you think you might deal with, and that's that, you know, that policy which could deliver a good outcome because of the uncertainties could deliver lots of different outcomes as well, apart from that good one. And I'm not clear how we give advice then to decision makers about these policies which could give good outcomes, but could also give bad outcomes. So there's a sort of a difficulty in the sort of advice we give, given the uncertainties associated with any one particular policy they take. They've got to make that decision in the end.
Yeah, I think there is. I think that is an issue. And I think decision makers don't like uncertainty. None of us like uncertainty. But I think if we can start to move people from the idea that we can tell you this is good or bad, to say there's a 60% chance this is good and a 40% chance it's bad, And we can possibly use the ideas of betting, that all decisions, in a sense, taking bets. And that's going to take a bit of education of decision makers. But I think in terms of probability, they probably wouldn't like it. In terms of betting, they might. That might be nearer to a real world thing, that if you make this decision, there's a 20% chance of a good outcome and an 80% chance of a bad outcome, and this other decision has a 30% chance of a worse good outcome, if that makes sense, and a 70% chance of a not so bad outcome. That you can start to balance that up. Now that's much more complex than saying this is a good outcome, this is a bad outcome, that's not one thing. But I think putting it in terms of betting might well get people to be able to make that sort of decision. We do this all the time with weather forecast. When we decide to take whether an umbrella or not, we do a sort of probabilistic calculation in our head. What's the chance that it's going to rain? Now, it's a bit more complex when you're working out the route of HS2, but I think we could go to a sort of more probabilistic way of doing it, which would include that uncertainty, so that you're quite right. If we do the same decision, it could go bad. Does that answer your question?
Yeah, I just think it's really complicated, and the sort of things you're talking about are interesting.
Thank you. Thank you very much for that. We have the next question from Paul Sweeney. I will unmute you so you can ask your question, Paul.
Yeah, thank you very much.
You're muted.
Hello?
Ah, you're back.
Yeah. Hi. As somebody who does use mathematical models to influence decision makers, there's one kind of critical thing which I think is often ignored, and that is the communication piece. Because if you really want to influence people making decisions, what you first have to understand is how they make their decisions and what information is relevant to them. And very often it's the communication of the results of your modeling is as important as the modeling itself, because you kind of have to speak their language if you really want to be able to get people who are not as adept technically as yourself to be able to understand what the issues are. So I think that's a very critical point of using models, and a particularly complicated models and models with uncertainty. Don't ignore that communication.
No, I agree with that, and including uncertainty in the way we talk about it is quite hard. Visualization is a little easier. I think we have some ways to visualize uncertainty, but we don't really have good ways to talk about uncertainty. Betting's not a bad one, but it doesn't really get the sort of full depth of what we're talking about, particularly when you get complex things not on a single number. And then visualization becomes incredibly difficult.
Mm.
You know, if you show a confidence interval to a decision maker, they're almost certainly going to misinterpret what you've shown.
Exactly. Yeah. I mean, I've seen uncertainty as well. That the other difficulty is the spread of results. Yeah. You know, this could be either incredibly damaging to the environment or completely benign or somewhere in between. You know, I've seen model output over 15 orders of magnitude, and that really does not help decision makers be able to understand the impact of what they're trying to do. You have to put it in terms which they really do understand.
Yeah, I agree with that, and I think sometimes if you've got 15 orders of magnitude, it's possibly not worth showing it to them, telling us much. And if that's the case, why do we bother showing it? You know, we ran a model, it didn't tell us much. That's not going to help.
Yeah, I agree.
Thank you, Paul. The next question is from Alex Hagen Zanker. I will also unmute you now so you can talk, please.
Yes, hello. Not really sure who I'm talking to because I can only see this one speaker at a time. But I've got two questions. One is, are you used to the situation that decision makers use your models, or is it more likely to be advisors to decision makers? Because that's my experience.
Yeah, it's almost certainly advisors to decision makers. So your model, that diagram that I was talking to Paul about, might percolate up and be used by the advisor to the decision maker to help the decision maker.
And my second question is, are they normally not more interested in understanding the problem and the different dimensions of the problem and trade-offs and synergies and things like that? So would they be interested if you said, no, this is the best decision and I'm 55% certain that it is, or would you like to have somehow more understanding?
I think understanding is part of it. Understanding is good, but sometimes things are not intuitive. So understanding is great if you have intuition and you can use intuition. But if things are non-intuitive, then just understanding the problem is going to give you a different answer to the numerical model, which in a sense is an encapsulation of our understanding.
But have you ever seen a decision maker accepting non-intuitive model results?
Oh, I can't think of one offhand. I'm a mathematician. I develop methods. I don't tend to talk to do real world things.
Okay, thank you very much, Alex. I have also another question, some questions on Slido. There is one question from Alex Comber. He's asking whether Pareto solutions are really equally good, and he's kind of mentioning endorsement theory as a route for handling qualitative uncertainty. He's mentioning Cohen heuristic reasoning about uncertainty and Pittman from 1985. So, I mean, a few hints to you. If you want to respond to that.
So they're not equally good, they're equally optimal, which is not the same thing. And that's an important distinction to make when you're optimizing, that optima aren't necessarily good. And I take the point about qualitative uncertainty, and I will dig out that book.
Okay, we have another raised hand from Nick's church. We have to, I think, try to make it a bit quicker because we are already behind our time. Yeah. So, Nick, please, you can talk now.
Hi, that was a really good talk. It strikes me that on the equally optimal solutions for this Pareto front, if we're kind of, whether we're working forwards or backwards, it's likely that these equally optimal solutions will actually have fairly similar and probably smoothly varying parameters that lead to them. And that strikes me as being a problem for decision makers in that their decisions are not really very different from one part of the curve to the other. Decisions. So how do we discretize and really clarify what's a different, distinct decision that leads to an similarly optimal outcome? Yeah,
I think this is the question of how you present that to the decision maker. I think you probably don't give them the Pareto front and say, here's the Pareto front. You would probably chop it up into chunks and present it that here in this region, this part of the decision is, this part of the outcome's dominating the other part, and in this part it's the other way around, and then to slowly zoom in rather than give them the smooth front. You're right, along that Pareto front, things are going to be varying smoothly, so small changes make little difference, and they're not going to be interested in small changes. They're interested in big changes because they want to make a big decision. So yes, there is a step between what I've described and what you would present to a decision maker, which is putting it in a form that they can understand and action.
And then, of course, we come to the same problem that we encounter in lots of other places of where do we draw those thresholds and how do we justify the motivation for choosing one number as our threshold from one side to the other or another.
Yeah, I think that's probably part of that conversation with the decision maker or the decision maker's aides. Yeah.
Okay, so one last question from Chris Dent, and then everyone else, if you have any questions, please put them on Slido, and then we might won't be able to come back to them later as well. So Chris, now your last question, please make it short. Thank you.
Yeah, this is probably one which Peter is kind of expecting because he'll have heard it from me a number of times before. But just following on from Paul's very good comments about communication and some of the discussion previously, I just want to emphasise the point that communication is a two-way process. Often it's thought that modelers produce evidence and then communicate it, but it's very important that modelers are doing modelling which is relevant to what the real world questions are about. And very often there simply isn't enough ongoing communication in modelling studies to make sure that the modelling outputs are as relevant as they might be, and therefore as worth communicating as they might be.
Yeah, no, I couldn't agree more.
Okay, thank you very much for all the questions.